The next and last big concept in this section is term-by-term differentiation and integration of power series. Now, I hope that in a couple of weeks you'll be able to look back and go, wow, that is crazy. Because once you see Taylor series and Maclaurin series and how they tie in, how everything we've been doing sort of culminates and it works towards us finding power series and ways to represent functions that we couldn't do before. So I'm going to skip over this. I suggest you pause and read over this at least once because it should make sense after we've discussed some other things. The idea is that if you have a given power series, if I have a power series here, in fact, let's just go ahead and think of it as this right here. I have this power series that represents a function f of x. Well, if I want the power series for f prime of x, then I can take the derivative of that power series term by term. So each individual term, I take the derivative of, and I get a new power series that represents the derivative. I can similarly, so here it is, you might see the power rule floating around in there. But the term by term, how it's written out with the constants, okay, this is important to note because the derivative here is just c1. The derivative here is 2c2. The next one will be 3c3, etc. Now we can also take the integral term by term. We start out with our function right here, and when we take our derivative, our integral, we get this guy right here, which is the reverse power rule. And again, there is a constant floating around here. C naught, x minus a, it gets a term it didn't have before. X minus a squared over 2, cubed over 3. So we have those same, that power rule for integration. Now we've also got this plus c, this big constant c. So never forget the c when you're integrating. Okay, so example 11. Use the power series representation of f of x equals 1 over 1 minus x. We know that very well. To find a power series representation for g of x, which is 1 over 1 minus x quantity squared. Okay. Notice that g of x equals f prime of x. Okay, so if we look at the derivative of our power series, I'm going to go ahead and write it out term by term. It is 1 plus x squared plus x cubed plus something else. Now if I take the derivative, that is 0. I'm going to go ahead and include that. Plus 1 plus 2x plus 3x squared plus, right there. Now what I want to do is write this in a closed form. And it may take some thinking for you to recognize what this is, but there is a pattern with the constants. We do have x to the n, but we're going to have an n plus 1 there. So if you plug in 0, that's 1, okay, with x to the 0, so that's just the 1 term right there. If you plug in a value of 1, that is 2, x to the first. Value of 3, that is 4. Wait, hold on. I said 2. Oh, that's 3. 3x squared. Plug in a value of 3. That's 4x to the 4. Or 3. So we have that building up there. So recognize the pattern. It's going, and that's the closed form right there. Now, one question we have is determine the interval of convergence. All right. Well, if our derivative, see, if our original function had an interval of a minus r, a plus r, that's where it's centered at a, then our derivative is going to have the same interval of convergence. All right, so this means, leave that underlined, that means that this is going to have an interval of convergence if absolute value of x is less than 1. Now let's actually look at the endpoints. So that would be -1 to 1. So if x is -1, then that makes our interval n plus 1 to the -1 to the n. Okay, now that is going to diverge, because it's an alternating series. where this is not decreasing, so that diverges. All right, what if x equals 1? Well, then that would be the sum of n plus 1, and that would be it. So that also diverges. So our interval of convergence is -1 to 1. And there is our power series representation for 1 minus x quantity squared. Now, let's use that to evaluate the sum of this series. All we really need to notice is that this series we're given is not a power series. It is just a series. And we can write this as n plus 1 times 1/4 to the n, which means x is 1/4. So this is actually the same as g of 1/4, which is 1 over 1 minus x quantity squared. 1 over 1 minus 4th squared. All right, 3/4 squared, that's 9/16, so 16/9 is the sum of that series. Number 12, for f of x equals ln of 1 plus x, find the power series representation using f prime of x equals 1 over 1 plus x. Okay, so let's begin with f prime of x. All right, f prime of x is 1 over 1 minus negative x squared. Oh, whoops, that's the wrong one. Negative x. Okay, so this is 1 over 1 minus negative x. So the representation of that would be negative x to the n. So term by term, okay, so f prime of x. Term by term, that would be 1 minus x plus x squared minus x cubed plus etc. So let's go ahead and take the integral of both sides. Okay, with respect to x. So this will give us f of x is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus etc. Now we want to have c, our constant there. Okay. Well, because this is natural log of 1 plus x, if we evaluated x equals 0, would tell us that we have 0 equals c plus 0, so therefore c equals 0. All right, so that means natural log of 1 plus x is, and we have alternating signs there, so this is the sum of n equals 1 to n equals 0. Now we'll leave it at 1. Okay, take care of the alternating. So negative 1 to the n plus 1, x to the n over n. Stare at that pattern for a little while and make some sense of that if it's not obvious at the moment. All right, last question in this section. For f of x equals tangent inverse, find the power series representation using f prime of x equals 1 over 1 plus x squared. So we've already dealt with this one. So let's start with f prime of x. All right, f prime of x equals 1 over 1 minus negative x squared, which is the sum, n equals 0 to infinity, of negative 1 okay, so we'll have negative x squared, so it'll be negative 1 to the n, x to the 2n. So in our closed form, that's what we have. So let's go ahead and write it out term by term. That is 1 minus x squared, okay, plus x to the 4th minus x to the 6th plus etc. Now we will take the integral with respect to x. So term by term, we get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7 over 7, etc. Now we need to have our plus c. Now the integral of that's f of x, which we're saying is tangent inverse of x. So tangent inverse of x equals that. Now tangent inverse of 0 is 0, which means our value of c is 0. So that tangent inverse x is just x minus x cubed over 3 plus x to the 5th over 5. Okay, now those are alternating signs. Alternating signs, and we have all odd exponents there. So negative 1 to the n. You have x to the 2n plus 1, and it's divided by each of those same odd coefficients, so 2n plus 1. Okay. And there we are. And I should probably note this is valid for absolute value of x less than 1, because going back here, this was for absolute value of x squared, negative x squared being less than 1, which is equivalent to the absolute value of x being less than 1. So since they are valid on the same interval, there we go. All right, that is the end of section 6.2. There's a whole lot here, so you'll probably want to take notes on this more than once. Okay, listen to this, listen to explanations a little bit longer than some of the other ones, because there is a lot. But that is the end of this section on power series. Let's see, and some of the properties we've got there. All right, that's 6.2.